Hello, guys. Welcome to another episode of Cuda Education. So today I want to just finish off a particular discussion we had. So you remember in the previous, literally the previous episode, we talked about near plane and far plane, right? And we had 0.1f and 100f as the coordinate system for the near plane and the far plane, and we had pictures and graphics showing the near plane and the far plane, and then we remapped that range between 0 and 1 for the normalized depth, right? And then we had our depth testing, which we use for depth testing to figure out, is this object behind or in front of another object? Are we going to render this object, or is this object being blocked by another object? And we could save on taking system time, energy, effort, resources, and memory to render this object if we don't need to because it's blocked, right? So we have two coordinate systems, and for this episode, what I want to do is reconcile the two worlds, right? So when we when we go further into it and we talk about the projection mapping. So in a typical perspective projection, the depth value is computed roughly like this. So this is the depth value. Then it gets mapped to a depth buffer space of 0, a range from 0 to 1, right? So this is sort of the math behind it, okay? So key variables: n is the near plane, and f is the far plane. So near plane is 0.1, far plane is 100, right? And that is consistent with what we have here, okay? And you were trying to basically take these values and then get it to a normalized value of 0 to 1, for 0 being near plane and 1 being the far plane, right? So so the Z view now is actual distance from camera, negative in OpenGL, but we'll think in magnitude. Okay, we're dealing with Apple Metal, but whatever. Actual distance from camera. Okay, so we have all of this, and we have this Z and DC. Normalized depth coordinate, is that what NDC stands for? Okay. So at near plane, Z equals N equals 0.1. So plugging in gives depth of 0. Okay. At far plane, Z equals F equals 100. Plugging in, we get a value of 1. So we basically want, when we yeah. The important part, non-linearity. The critical term is 1 over Z. So this is why depth is not linear. Example with numbers. So 0.1 as the distance, the depth value is 0. 1, it's this. 10, it's that. And then as we get closer to our value, our maximum value, we get 1, right? So it's a plug and play kind of thing. Insight, notice this. From 0 to 1, huge depth change. From 1 to 100 barely changes, right? So this is what we talked about, I guess, the right. So this guy right here, one to right. So you notice from 0 to 1, we get a huge change, but then from 10 to 100, we get very small changes on the depth value. So I guess this is where it's talking about the precision. Why your diagram shows both values in your image 0 to 100. Compressed depth values. Okay. Okay, right. The depth buffer is zoomed in near the camera and squashed farther away. So basically, um, like from 10 to 100, we really don't care about, what's, what's going on out here because that's farther away from the camera. Okay. But when we're getting closer to the camera, you see just for a point 0.9 difference from here to here, we get the majority of the depth values precision as we get closer to the camera, and that makes sense because we are we're more concerned with what's going on closer to the camera than farther away from the camera. So this is why we say it's nonlinear. Yeah, now I follow. This is why we say this is nonlinear, because closer to the camera we really zone in on the granularity of what's going on. But as we get farther away from the camera, we don't care. Because it's farther away from the camera. We're rendering less detail, all of that stuff. So our point becomes what? Is zoomed in near the camera, squashed farther away. Why this matters? Practical. This causes Z fighting far away. Objects at 90 and 100 might map to nearly the same depth, flickering. Yeah. Yeah, but anyway, guys, I just wanted to at least add this to the conversation. Um, obviously we can't go too deep into it right now, but one liner takeaway: 100 F is physical distance. 1 is the compressed result after a nonlinear projection. Um, right. So because we have so little granularity between 1 and 100, you know we basically just have a point 0.1 distance. We might get flickering. We might get yeah. Yeah, but like we can't afford to we need more granularity closer to the camera, because we're going to experience, we don't want the flickering. We want to have a we want distinction between any small difference in distance closer to the camera. But as far as the stuff farther away, we really don't care. That's my read of it. I might not be entirely correct, but that's my intuition. We need more precision as we get closer to the camera, because first of all, the observer, which is you, you are looking more closely at what is nearer to you, and you will observe things better, what is nearer to you, and you want more detail, and you want more difference in terms of knowing what blocks what, in terms of you know depth testing and things of that. But as you get farther away, we don't really care, right? So there's less granularity as we get farther away, right? So the difference between here and here is very big, but the difference between here and here is very small, right? So the difference between here and here is big, the difference between here and here is very small, right? It's just literally 0.1 difference, whereas this is 0.9 difference, okay? So that's my read of it, guys. This is Cuda Education. Support the channel. You know what to do on the YouTube. Tell your friends. We're in the first quarter of 2026. Just finished, basically. So get on the bandwagon before the year is over, because by the end of 2026, we want to be in a different place as it relates to Apple Metal. Thank you guys for watching. Have a great day.